Let us see our first question. Write the rate expressions for the following reactions in terms of disappearance of reactants and appearance of products. See the first question. In seeing the first question, you will come to know that all the coefficients are 1 only. So it is easy to write the rate with respect to reactants and products. So before the reactants rate expression, we will put minus. For the products, it is plus. So the strategy should be important to know the stoichiometric coefficients. So we wrote the right equation, that is minus delta I minus by delta T minus delta OCl minus by delta T for reactants, delta Cl minus concentration by delta T, and delta OI minus by delta T for the products. So it is all equal to each other. Why? Because it is a stoichiometric rate expression. Moving on to the second equation, we have ammonia and oxygen reaction is there. And these coefficients are 4 for ammonia, 5 for oxygen, 4 for NO2, NO nitric oxide, and 6 for water are there. Before the rate of this ammonia, I will put the reciprocal is minus 1 by 4. Reciprocal of 4 is minus 1 by 4. That is the coefficient of this rate of ammonia. And coefficient of rate of oxygen will become minus 1 by 5, as 5 is the number of moles given in the oxygen. That is nothing but coefficient of oxygen in the balanced equation, and that is minus 1 by 5 delta oxygen by delta T. Whereas nitric oxide, if you take this plus 1 by 4 delta NO concentration by delta T, we got where that water we got 1 by 6 delta H2 concentration by delta T we got. So what is the strategy is the reciprocal of the stoichiometric coefficient should be written. That is the rate expression for reactants or products if the coefficient is other than 1, okay, in the balanced equation. Let us move to the next one. Consider the reaction 4NO2 plus O2 gets to 2N2O5. Suppose that a particular moment during reaction, molecular oxygen is reacting at rate 0.024 molarity per second. At what rate is N2O5 being formed? At what rate is NO reacting? So they are given oxygen rate. So using oxygen and nitrogen rate expression, stoichiometric expression, minus delta oxygen by delta T will become equals to 1 by 2 N2O5 delta T. So the given value is nothing, oxygen value substitute in this expression. The 2 will be multiplied. 2 into this value got 0.48 molarity per second is the N2O5 rate, that is appearance of N2O5 in this reaction. Moving on to the second question, at what rate NO is reacting? So NO2 is reacting. NO2 and O2, if you write the stoichiometric rate expression, then it will be minus 1 by 4 delta NO2 by delta T became equals to minus delta oxygen by delta T. So oxygen value we know. So that value if you multiply with the 4, you will get NO2 value. We are putting minus because NO2 is a reactant. So this is the simple problem. First problem we discussed. Simple problem category. Next, the reaction of nitric oxide with hydrogen at 1280 degrees Celsius is given like this: 2NO plus 2H2O is 2 gives rise to N2 plus 2H2O. They are given a data which is collected at this temperature, and using this data we have to find the rate law and also rate constant as well as rate of the reaction. If NO concentration is 12 in 10 power minus 3 and H2 concentration 6 in 10 power minus 3, at that time we have to find the rate of the reaction. But for the first question, rate law, we have to see the entire experiment data information. If you see the 3 experiments, in the first 2 experiments we have H2 concentration given same, and using first 2 expressions you can find the NO power, and we can use the second and third experiments data information. NO concentration came constant, so that time we can find the power means order of H2 in the rate equation. So we'll go through that one. So experiment 1 and 2, if you take the values upon dividing the rate of experiment 2, second experiment data with first experiment data, we got 2 power x is equals to 4. That means x value got 2. Meaning is nothing but nitric oxide power is 2, means order with respect to nitric oxide we got is 2. And experiment 2 and 3, if you take, the hydrogen concentration is given, see, differently, but NO concentration given constant. So these values if you take, we got 2 power y is equal to 2. Y we are considering as the order of hydrogen, order with respect to hydrogen, that we got is 1. Thus, we have order with respect to NO, order with respect to H2, got, that is substituting the formula. Got rate law is K into NO, rate is equal to K into NO power 2 and H2 power 1. Overall order is third order reaction. Now, the second question is to find the rate constant. To find the rate constant from the rate law, equation is rate by NO concentration power 2 into H2 concentration. The value substituted from the data information, we got rate law, rate constant as 2.5 into 10 to the power of 2. That is mole square, 1 by mole square per second. So this is the second one. Third one, rate of the reaction, but they are given the concentrations in the problem, specifically for NO is 12.0 into 10 to the power minus 3 and H2 is 16 10 to the power of minus 3. That value substituted with the rate constant obtained in the problem number 2. That is giving 2.2 into 10 to the power of minus 4 molarity per second is the answer for the rate of reaction. So 3 problems asked in this question, 3 calculations. The first calculation we done is rate law. That is we got is rate is equal to K into NO power 2 into H2 concentration. The second question is rate constant. We calculated the rate constant using this expression and substituted the values from the data information, we got rate constant. Third problem they asked, calculation asked is rate at a particular concentration of NO 12.0 10 to the power minus 3 and concentration of H2 16 10 to the power minus 3. That time this value we got is 2.2 into 10 to the power minus 4. So this is our next question. So let us see the next one. The conversion of cyclopropane to propene in the gas phase is first order reaction with a rate constant of 6.7 10 to the power minus 4 per second at 500 degrees Celsius. So they are very clearly telling it's a first order reaction. So for first order reaction, we have a mathematical expression. Using the mathematical expression, you have to find the time, you have to find the concentration at 8.8 minutes. First question. Let us see. Say if you apply this first order rate constant expression, here we have given one calculation, or else you can also use the general calculation you have, that is log A by A minus X, or you can write log A naught by AT, that is equals to K into T by 2.303. Here you need this AT only, right? Then what is the value of A naught by AT? That will become equals to 10 power KT by 2.303. Then after you will find AT. AT is equals to, what is AT value? That value is equals to A naught into 10 power minus KT by 2.303. So this is our general equation, I am telling. So the same thing if you apply here, you will get the answer as 0.18. But here minutes is converted into seconds. That is the first question. What is the second question is how long will it take the concentration of cyclopropane to decrease from 0.25 to 0.15? Here also we'll use the same expression, mathematical expression. In that expression you have to find the time interval. So what is the formula here we are using? A simple calculation when we have e power all these things. So that T is equals to ln A naught by AT into 1 by K. Okay. We'll use this expression. What is the actual expression is this one we have shown. Actual expression is ln AT is equal to minus KT plus ln A naught. This is our expression. And this one we have obtained. What we have obtained from it is ln AT is equals to ln A naught minus KT, right? From this only this is they have got T they want. So what is the KT from this? KT is equals to ln A naught by AT. Now in this we want K, what is T? T is equals to 1 by K into ln A naught by AT. A naught is 0.25, AT is 0.5. And what is the K value is 6.7 10 power minus 4. If this is substituted, then you got 13 minutes. Next question, they are asking us to find the time interval. The third question, they are asking us to find how long in minutes will it take to convert 74% of the starting material. Starting material is 100%. And that is converted to 74%. Mean it became 26 A minus X means AT value 26 or 0.26 when you take A is 1. So that is substituted. We got 33 minutes. So in this expression, you have to find the time interval. So AT value is how much? 26 and A naught value is 100. You write 26% also okay. So you got 33 minutes. Next question. The rate of decomposition of azomethane is studied by monitoring the partial pressure of the reactant as a function of time. So in this the data information given, the time intervals 100, 150, 200, 250, 300 like that, and partial pressures given. Partial pressures and concentrations are directly proportional each other. So you can use partial pressures in place of concentrations. A naught will write P naught and AT will write PT. Let us see. The question is determine the rate constant. That is a question for this one. If it is a first order reaction, we'll check it. If it is gradually decreasing with time increasing and concentration is decreasing, means it's a first order reaction only. If you find the slope of this one, the values, taking the values, then that we got is after plotting the graph, we got slope value is minus 2.58 10 to the power of minus 3. So I have to write the data on x-axis. You have to take this data information time. On y-axis, you have to take these concentrations. The slope we have calculated is this value. So that is matches with our ln AT expression. Ln AT is equals to minus KT plus ln A naught. In this, the slope is minus value we have. So that is equated to this one. You got same value with positive answer. Okay. This is our answer for this one is 2.58 to the power of minus 3. We have to put the graphical representations. Next question, the decomposition of ethane to methyl radicals. Ethane to methyl radicals is a first order reaction with the rate constant 5.36 into 10 to the power of minus 4 second verse. And they are asking us to find the half-life of the reaction. You know half-life formula? That is T of is equals to 0.693 by K. And this if you substitute, you will get seconds answers. The seconds will be converted into minutes by multiplying with 1 by 60. Then you will get 21.5 for this problem. Next question. Iodine atoms combines to form molecular iodine in the gaseous phase like this. It's a second order reaction, and the high rate is 7 10 to the power of 9 is there for this at 23 degrees Celsius. First question we have to find, that is initial concentration of 5 if you take 0.086. Then you have to calculate the concentration after 2 minutes. Let us see. This is the actual expression for second order rate constant, second order expression. 1 by AT minus K is equal to KT plus 1 by A naught. That A naught value given as 0.086 in the problem, and K value given as high value 7 10 to the power of minus 10 to the power of 9. Whereas time given 2 minutes converted into seconds. Then after that AT upon solving the equation, you'll get 1.2 in 10 to the power of minus 12 molarity. It's a very low value in the concentrations. It is undetectable also. Very large rate constant for the reaction means practically at all the iodine atoms combines after only 2 minutes of reaction time. Okay. Next one. What is the second question they have asked is, calculate the half-life of the reaction if the initial concentration of iodine is 0.6, one value. If it is 0.42, another value. So two values of half-life you have to calculate. If it is 0.60, then the second order reaction half-life expression is 1 by K into A naught. In that, if you substitute 0.6 and K value, and you'll get 2.4 at 10 to the power of minus 10 seconds as the half-life at initial concentration 0.6 for iodine. If other question they are given, another problem they are given in that one calculation, that is 0.46 they asked to take as initial one at the same rate constant, asking half-life. That half-life we got is 3.4 at 10 to the power of minus 10 seconds. You can check it off in your calculation. So this is the answer. So in that way, that question can be solved. In this we have two calculations are there. The one calculation is concentration after a particular time interval. Another calculation is half-life after initial concentration, particular initial concentration for the second order reaction. Okay. Let us see the next question. The rate constants for the decomposition of acetaldehyde are measured at 5 different temperatures. These are the rate constants. Here they have given us that rate constants. Here rate constant 1, 2, 3, 4, 5 given there. And temperature 700, 300, 730, 760, 790, these are increasing. Rate constants also increasing. So it is direct proportionality is there. But they are telling it is a 3 by 2 order, which is fractional order. That's why the units also given as 1 by molarity power 1 by 2 into seconds. But let us see, our YRK'S expression is can be taken because they are asking us to determine the activation energy. Okay, and this YRK'S expression logarithmic form ln k is there. That ln k can be obtained from these values. So that value we have taken in the graphical representation, and also with the temperatures we got the different values. Temperature 700, 730. These values using this one we got 1 by T values also. That were taken on the x-axis and 1 by T taken x-axis and ln k is taken on y-axis. So y is equal to mx plus c. We got negative slope here. That's why the curve got like this. This is the slope calculation. If you observe, that is y2 minus y1 by x2 minus x1. That slope we got minus 2.0 10 to the power of minus 10 to the power of 4. From this expression, minus Ea by r is the slope. That Ea by r is equated to this number. And substituting R value of that, we got this activation energy answer as equals to 1.74 10 to the power of 2 kilojoules per mole. Hope you understand. Taking the values and drawing the graphical representation, you will come to know that what is the slope of it. That slope is equated to YRK'S expression of Ea by R. then after we can easily find what is the value in that case. Okay, so finally we got this is the answer for activation energy of the reaction. Next one, the rate constant of first order reaction is, the rate constant of first order reaction is 3.46 in the power of minus 2 second per second at 298 Kelvin. What is the rate constant at 350 Kelvin if the activation energy of the reaction is 50.2 kilojoules per mole? So here we have two temperatures are coming and one rate constant is there. We have to find another rate constant using this value. So logarithmic form of Arrhenius expression, if you write in that, if you substitute K1, K2 values, K1 if you take 3.46 at the temperature T1 298 Kelvin, another temperature will become 350, which is given the problem. That temperature we don't know rate constant, that is considered as question mark. So the value substituted and that kilojoules value of activation energy given the problem is converted to joules as R value is there in joule per Kelvin mole. So it is 8.314 R value substituted upon simplification. Finally, we got K2 values 0.702 per second. This is the most important board examination for as a problem, 3 marks problem. Yeah, let us see the key equations in this one. What are the key equations we have discussed in the chemical kinetics is the rate law expression. Rate law is equal to K into A power X into B power Y. The sum of these gives the overall order of reaction X plus Y. Ln AT by A naught is equal to minus KT. This is the relationship between the concentration and time for first order reactions. And if you convert this one into Y is equal to mx plus C formula, then this will be a graphical representation using the rate constant slope of this reaction. And half-life of the first order reaction expression given is 0.693 by K, which is also the most important one for problems. Come to the second order equation, we have 1 by AT minus is equal to KT plus 1 by A naught, which gives the relationship between the concentration of time for the second order reaction. And this can also be taken graphically, and that time the slope can also be calculated in this second order. Come to the Arrhenius expression we given is K is equal to A to the power of minus EA by RT, which is the Arrhenius equation expresses the dependence of rate constant on activation energy and temperature. The other one we are given is logarithmic form of Arrhenius equation with the only one temperature is used. Ln K is equal to minus EA by R into 1 by T plus ln A. That is the equation for graphical determination of activation energy. Using this one also we have calculated the activation energy. And one more equation we again is ln K1 by K2, that is equal to EA by R into T1 minus T2 by T1 T2, which is called the relationship of rate constants at two different temperatures. Using these expressions, we have taken the problems and their solutions. Okay. Okay, thank you very much, dear students and friends. I hope you observed the different problems what I discussed in this session. Hope they are useful. These problems are useful for the students who are seriously preparing for examinations, coming examinations. Okay. Thank you very much for being with me in this short session. This is the lecture number 5 in my chemical kinetics, the problems, theoretical problems. That means only board level problems I have discussed in this lecture. Coming classes, I will discuss objective questions also, as I have given you the important concepts of objective questions on this chapter in the previous session. Until bye bye. Thank you.